I'd like to welcome you to the second Zurich keynote by Julie of Haskell book fame, and she's going to talk about teaching Haskell for understanding. Okay, let's go.
Yeah.
Good luck.
All right. Can everybody hear me okay? Okay. So yeah, I'm here to talk about teaching Haskell for understanding, and the for understanding part I think will become more clear as we go through the speech. But I'm not here to talk about teaching Haskell for any other purpose besides understanding. So I'm not here to tell you how to evangelize Haskell at your workplace, for example, and that's something that I don't really know anything about. But so. Oh, we must have gotten the wrong window in focus. Hang on. There we go. So yes, my name is Julie Moronuki, and I am one of the authors of Haskell Programming from First Principles, which is more commonly known as Haskell book. So some of you may already be familiar with this story. If you are, bear with me for just a few minutes. I met my co-author, Chris Allen, on Twitter in 2014, and prior to that time, I had never been a programmer before and was not even interested in being a programmer. I had been a linguist, and I had studied philosophy, and I had been a librarian, and I had been a teacher for a very long time. And I had no interest in becoming a computer programmer. And Chris, who had a lot of interest in teaching people Haskell, sort of persuaded me to study Haskell because he really wanted to have the experience of teaching Haskell to a non-programmer and seeing how it was different from teaching Haskell to people who already had programming experience. So finally, I gave in. I said, okay, I'll try it. I don't think it's going to work. I don't think I'm going to like it, but I'll try it. And I sort of poked along at learning it, not very wholeheartedly, but I poked along at learning it, and I was working through Learn You a Haskell, and then we would talk over Skype and stuff so he could answer questions, right? So we lived quite far away. And then one night, I was listening to a talk. I think it was a Strange Loop talk by Paul Snively and Amanda Lauker, and they said in the talk, it was about type systems, and they said in the talk, this quotation that I believe came from Yaron Minsky, but I can't actually find the original source, that the purpose of a type system is to generate legal programs, right, and to make any illegal states unrepresentable. And this was sort of the big turning point for me, because I thought, yeah, this is just like generative syntax, which is what I had been working on in linguistics in graduate school. So that interested me a lot. And I don't think there's any other programming language that could have gotten me interested in programming, to be quite honest. But the similarity with generative syntax was exciting for me. So when I started graduate school, or when I was in undergraduate and then started graduate school, the tree that you see on the left here, this syntax tree, is how we used to draw syntax trees of English sentences. So you see at the top, you have an IP, right? And each one of these nodes is meant to represent, a phrase, right? So the IP would be the largest phrase, right? That's the inflectional phrase, or what we might think of as a sentence. Some of you, if you're familiar with linguistics, some of this explanation is going to be a little bit hand-wavy, and I'm going to completely gloss over all of the arguments about between the different schools of generative syntacticians, because it doesn't matter for right now. And then we have, an NP with an I bar, right? So the NP is the noun phrase, and that's going to be the subject of our sentence. The I bar is the rest of the sentence, right? Because we want all of these to branch in a binary pattern. Where you see the N bar, that's a place where it could branch. And this one doesn't happen to, but it could branch there. Right? The transformation rules that turn this kind of theoretical syntax tree that gets projected out from words, or that's the theory. The transformation rules that turn those into sentences are recursive, right? So every sentence is theoretically potentially infinite, right? Obviously, the human limitations on speech and understanding prevent infinite sentences. But at any place, these could branch, right? So we have these bars where they could branch. And so this branches into the sentence, he studies linguistics at the university. And the V, of course, is for the verb, and the P's are for prepositional phrases, right? And so different words have different phrase structures or argument structures. And I particularly worked on the argument structure of verbs. My language-specific research was in a Native American language, and I researched the argument structure of their verbs. But this is really an exciting sort of research, because the goal here is to find what connects all human languages universally, right? I mean, that's the goal. We're still a long way from that goal, but that's the goal. And to come up with a set of rules that are abstract and general enough that they could potentially, if you knew all the implementation details of a certain language, could generate all the legal sentences and only the legal sentences in a specific language. So eventually, by the time I was leaving graduate school, my syntax trees started to look like the tree you see on the right, which you can see what we've done, I think. We've kept the binary branching structure, right? That's the pattern that we care about. We've abstracted out all the other implementation details, right? We no longer care if, I mean, we do care at some level, but this allows us to talk about things in a very abstract and extremely polymorphic way, right? And so perhaps if you look at the work that I was doing in graduate school, you can see that this idea of finding a pattern and abstracting it out as much as possible so that we can talk about things in the most general and abstract way that we would ever want to, you can maybe see why Haskell appealed to me. All right, so that's how I came to approach Haskell. And that has influenced, for me, the way that I teach Haskell and why I teach Haskell. All right, so when I got the email asking me to give a talk about teaching Haskell here, for a long time I thought I had no idea how to approach this topic, right? The topic is very broad. There's all kinds of different teaching. We teach face-to-face. I usually teach face-to-face. When we teach in meetups, it's less intense. If you're teaching training, then it's more intense, right? You can teach through blog posts. You can teach, and should teach, please, through documentation. You can teach by answering questions on forums like Reddit and IRC. You can teach through conference talks and the like. So there are a lot of different ways of teaching, and they share some things in common, and they also have differences. And so I was trying really hard to think, what's the approach that I want to take for this talk? What I finally realized is that there are two questions that people ask me all the time. When I meet new people in the programming community, and I've only been in the programming community for a couple of years now, people ask me all the time, what are you building? Right? It's a really common question. And people that I'm going to start teaching Haskell to, or people who maybe have heard of Haskell, and they're kind of interested, but they don't know if they should learn it, they ask me all the time what Haskell's for. I always find the second one to be a really interesting question, right? What are they really asking me? So what I'm first going to talk about, these are the two questions then that I decided to use as the kind of motivation for the talk that I'm actually going to give, which is mostly focused on why and how I teach Haskell. So we'll start with the whys. Yeah, what are you building? This is an interesting question, and it's a difficult one for me to ask. This question has always intimidated me a lot because I'm not a professional software developer. I'm not really building anything all that interesting, except for books. I write books, right? And those are actually fairly large projects. And but I think that really the answer for me is that by teaching people, I'm building up the community. Teaching is building a community, right? And for me, that's the important thing that I'm building. I do write Haskell programs. Most of them are either for my own personal use or enjoyment or learning, or they're things that I'm writing specifically with the goal of teaching other people something about Haskell, right? But these to me are the important things that I'm building. So, I'm going to be borrowing a lot in this talk. A lot of my ideas about how and why to teach Haskell have come from mathematicians, particularly William Thurston and Eugenia Chang. And I'm big fans of both of them. And so I'll be quoting them, citing them pretty heavily throughout the talk. So in his fantastic essay called On Proof and Progress in Mathematics, William Thurston says that the role of mathematicians isn't really just to prove new theorems. That's important, but new theorems don't actually bring new knowledge to the world or new understanding to the world unless people understand them. Other people, not just the person who proved it, right? If the only person who understands the proof of a theorem is the person who did it, then you haven't really brought anything new to the world. So the important thing that mathematicians do is find ways for people to understand and think about mathematics, to increase the human understanding and acceptance of mathematical ways of thinking. Now, all the fame and awards and credits will go to the theorem provers, just like when people ask, what are you building? They mean, what are you building in terms of what programs are you writing, right? That's what people really care about. But I'm not doing that. So I'm spreading Haskell's ideas. So the Haskell teacher, instead of helping to spread mathematical ways of thinking, well, actually it does spread mathematical ways of thinking, I suppose, but we're spreading new ways of thinking about programming. Most of the people that I teach Haskell to are already programmers. Oh yeah. Most of the people that I teach Haskell to are already programmers, so I'm teaching them new ways to think about programming. Most of my students program mostly in Java or JavaScript, right? So for them, a lot of Haskell's ideas are really quite different. And I find that even though most of them don't expect to ever go on to write Haskell professionally, they really want to understand the ideas. Right? There's a real hunger for understanding the ideas and for finding new ways to think about what they do, even if they can't use them professionally. So, all right, so teaching people the ideas about programming that Haskell represents makes those ideas more accessible to more people and spreads understanding, right? So proving theorems is good. Spreading understanding of theorems is also good, right? Those things together are what increases the amount of knowledge and understanding that we have in the world. I get a lot of pushback sometimes, particularly on Twitter, from people who think that community is not important. They don't care about the community. They don't learn a language for the community, right? They learn a language for its perceived technical superiority, for its performance, right? For its coolness, definitely. I sort of beg to differ. I don't sort of beg to differ. I absolutely beg to differ. Community is more than just what you think of as people being friendly, although that can be part of a community, right? So like Rust and Ruby in particular have made part of their community mission to be welcoming and friendly to newcomers, right? And the Ruby community seems to have made it a particular goal to like help people get something built fast, right? You don't even need to understand how Rails works. Let's just get something going fast. So that's an emphasis that they have in their community. We have a different emphasis in this community, right? The things that the Haskell community cares about are things like mathematical understanding, correctness. Some of us care about performance, some of us care less about it. But those are things that our community cares about. And, but there's more even than that, right? That's part of the Haskell culture, but there's more even than that. Your community is also the hallway track when you go to a conference, right? And all the great conversations that you have with people who just bring a different perspective, whatever language they write. So I had a really great conversation at the last conference I went to with the person who writes APL for a living. and we talked about, it was interesting because in Haskell we have arguments sometimes about whether or not the symbols, right, we use so many infix operators that are symbols, and whether or not those make Haskell harder to read. And obviously an APL programmer has a different perspective on that because they use more than even we do. Bless their hearts. So the hallway track, though, that's part of our community. Another part of our community is just all the stuff that exists before you ever started learning the language. I've made a joke before that all of us in this community are building our software on the backs of the Simons, which seems a little unfair to the Kevins and Phillips and all the other people who've been involved in making Haskell itself, in making GHC, Cabal, and Stack, and all the other stuff that we're using every day, right? So we are already in a community that is full of great people and great software. All of those things are part of your community. So there's this, oops, that one. So there's a Bill Joy, who is the co-founder of Sun Microsystems, said that no matter who you are, most of the smartest people work for someone else. He actually said this because Bill Gates was saying that he owned all the IQ in the world, right? And Bill Joy said, oh, no, right? So he went on to say that it's better to create an ecology that gets all the world's smartest people toiling in your garden for your goals. If you rely solely on your own employees, you'll never solve all your customers' needs. And I really think that that's true. The more people's IQs we get working on Haskell in any capacity, the better it's going to be. The better all of it's going to be. We were just having a discussion about tooling, right? The more people we get working on tooling, because tooling is actually a really big, and making an IDE, that's a really big project. The more people we have who are interested in it, the more likely we're going to be to get good tooling. Okay. All right, so the second question is, what am I ever going to use this for? Or the second question that motivates the why I teach Haskell is when people ask me this question, right? I get asked this a surprising amount. I find it to be a very difficult question to answer because Haskell is useful for so many things, right? It's just a general purpose programming language. You use it to write software. If you want to write software, you could use it. Okay, there's some kinds of software that it's not quite as good for, perhaps, because of the garbage collection or whatever, right? But it's general purpose enough that it seems like a strange question. But I started to think that it's, that what people are really asking me for, what it's for, is the way kids ask why they have to study math. Do any of you have kids? Okay, not a lot. But maybe you remember when you were in school, I don't know, maybe a lot of you really loved math the whole time you were in school, so maybe you never asked this. But you hear kids a lot who ask, well, why do I have to study math? What am I learning this for? What am I ever going to use this for, right? So we tell kids, oh, well, someday you'll use it to, balance your bank accounts, or you'll use it to understand how sales work or your tax forms, right? I mean, these are things that kids don't care at all about, right? That's not the answer that they're looking for. That's not the answer that that's gonna make them interested in math, right? So sometimes I feel when people ask me what is Haskell useful for, what they're actually asking me is the same question that kids ask their math teachers. And indeed, sometimes people do ask me, well, when am I ever actually going to use monad, right? The best answer to that question is code examples, not anything involving endofunctors or food analogies, right? The best answer to the question, when will you ever use monads, is just some code examples, and we'll look at that in just a little bit. All right, so some of you may or may not know this about me, but I homeschool my children. So I've homeschooled my children for every year of their education except for one. And my kids are now 12 and 8. My kids have never asked me why they study math. My kids have always thought that math is really super cool. The coolest thing, that's always the first subject that they want to do when they get up in the morning. It's the first thing that they want to do in school. And one time there were some people arguing on Twitter or something, and I asked my 12-year-old, I said, you guys have never asked me why you study math. What do you think about that question? Like, if somebody asked you that, how would you answer? And he said, well, that's a sort of strange question. We study math because it's awesome. He said, we study math because it helps us to understand the world. We study math because it helps us find patterns and beauty in the world. I'm expanding a little bit on what he said. He mostly cared that it's awesome, right? But so when they were toddlers, I started them with things like this. So understanding tessellations, finding the Fibonacci spirals in nature. We started talking about, how to, if you're making like a flip book or an animation, how to make sure that the characters grow or move in a kind of appropriate looking fashion, right? These are actually all mathematical, but they don't seem like math. They don't feel like math. But the connection between those things and what we then have studied in more formalized math has seemed sort of natural to them because we started so early and because it was always about fun for them, right? This is fun, right? This is good math to introduce your toddlers to. Okay, so all right. So since I wasn't a programmer before I started learning Haskell, this has always been the thing that's beautiful about Haskell to me. There's a lot of practical stuff around Haskell that I don't care very much about because to me, Haskell is a way to find beauty and patterns in the world. To me, it's connected to the beauty and patterns that I see in natural language, in formal logic, in mathematics. To me, these are all the same thing. So I can teach you how to build very normal sort of applications in Haskell, not web apps. I don't do web apps. But if you want to build a command line application, I can teach you how to do that. But that's not actually why I teach Haskell, and that's not my real goal. My real goal is to help people find the meaning and patterns in the world. So William Thurston, again, said, doing mathematics has the feel of fanciful invention, but it really is a process of sharpening our perception so that we discover patterns that are everywhere around. Right? Haskell also often feels like magic to people. I know this because they tell me that all the time. Oh, monads just must be magic. Monads are not magic, they're just math. So, Haskell seems particularly well suited to me to introducing people to these patterns. For example, in real-world Haskell, I love this quotation. As some of you who follow me on Twitter know I love monoids. So they said, monoids are ubiquitous throughout programming. The difference is that in Haskell we recognize and talk about them. But that's a really important difference. Being able to talk about them, to name them, means that we find them in more places, right? So this to me is exactly the same reason why we teach, or why I taught my kids math the way that I taught them. Okay, so that's enough about why I teach Haskell the way I do, and my priorities in teaching Haskell. Now, my students, fortunately, share many of my same priorities. Like I said, they don't necessarily believe that they will ever use Haskell professionally, but what they want to do is understand new ways to think about programming and to start finding those patterns. Now let's start talking about the process of teaching. So this is the how. All right, briefly, teaching should help guide a student from knowing something is true to understanding why it's true, to eventually internalizing the truth of it so that it has the quality of an insight or an intuition, right? This is the goal of teaching. Sometimes you can't get them all the way to the bottom step, but at least they need to understand why it's true. One of the big failures of mathematics education, at least in my country, I don't know about yours, one of the big failures of mathematics education is that we tend to stop at knowing something is true. So you're presented with these things that you're supposed to memorize and accept that they are true, and you never get to understand why they're true. And you certainly without some kind of other support system, you certainly never get to internalize the truth of them. And in fact, you're not supposed to, for example, when you're studying math, you're not really supposed to ask why we study math, right? You're supposed to, or to ask why something is true. A lot of your math teachers, at least again in my country, can't tell you why something is true. They don't know anything more than just the textbook has printed, right? And a lot of them, to be quite honest, are afraid of math as well. So you're not really supposed to ask, and that has the effect of eventually making math seem very autocratic, right? Just people are forcing you to just accept these truths and not tell you why, and they don't care if you understand. You just have to accept it. I think Haskell also feels that way to a lot of beginners. They're just told that monads are important. But that's not a very satisfying answer when people ask you why they should learn something. From a human perspective, the understanding is much more important. So in the last chapter of How to Bake Pie, Eugenia Chang talks about what she calls 3 aspects of truth. And they're basically what I just outlined, right? That there's knowledge, and knowledge is what we can objectively convey to the world through mathematical proofs or logical proofs, through code, right? Through, sometimes through natural language, right? You can convey facts, say about history. Understanding is why the facts are what they are. And belief is internalizing the truth of it. It's the insight or intuition that makes you really understand it and really take ownership of it. So, knowledge is what the outside world knows. Belief is your subjective or internal knowledge. And understanding is sort of what holds them together. When we talk about belief, it's important to understand we're not talking about this kind of belief, right? Haskell's not a cult. It could be. I think it would be a great cult, but it's not a cult. We're not talking about this kind of belief. We don't need to talk about belief in the same way we talk about other internal or subjective things. All right, so belief in this sense, belief in a piece of code or in the proof of a mathematical theorem is not the same thing as believing in love, right, or believing in God, right? It's something that you know to be true, you understand why it's true, and so now you've got a hold of the insight or the illumination that gave rise to it. Okay, so one of the interesting things about teaching is that teaching is sort of the opposite process of inventing something. So invention, or whether it's inventing a new proof of a theorem or inventing a new program, starts from a belief. It starts from an insight or a belief that you can do something, right? So Eugenia Chang talks about how she often feels like she has to do math twice. Once in her head, when she gets this sort of insight that something should be true, but she doesn't quite understand it yet, and then she has to work through the understanding, and then she can formalize that in a proof, and that proof becomes knowledge. So she sends her proof off into the world, and then teaching has to go through the opposite process, right? Teaching has to take that bit of knowledge and help the student understand it, and then reach the same point of insight that she reached when she invented it. And we have to do the same thing when we're teaching programming. Right? Makes sense. Proofs are programs. Programs are proofs, right? All right, so the trouble with, I don't have any idea how I'm doing on time. So the trouble with proofs is that when you move through this process of invention, when you move from having the insight to understanding it deeply and to formalizing it, you lose, right, in the formal proof, you lose a lot of the subtleties that gave you the insight in the first place. And so teaching is the process of helping students recapture those. Do you know how am I doing on time? Huh? Okay, Thank you. Okay. So now you've heard about why I teach Haskell the way I do, what my priorities are, and what the process of teaching is supposed to accomplish. So let's look at some examples. All right, so for creating understanding, I've picked just a few examples that I think are, that not everybody thinks about to illustrate. So for one thing, it's good to give an overview of something before you start diving into the details. So it is good to use concrete examples, but you want to start from an overview of what something is about or what something is for. This is particularly important if you're teaching somebody how to use, say, a large library or program. Okay? Giving them an overview first of what the whole program is supposed to do will help them understand then how all the different parts connect. So do that before you dive into the details. Secondly, provide rationales and examples that answer why a thing exists, why it's true, or perhaps, if you're talking about library documentation, why you wrote it the way you did. I don't mean you have to justify every time you use a case expression instead of a guard or something like that. I mean why you made some of your important choices, right? Encourage experimentation and hypothesis formation. So we tried to do this a lot in Haskell book through the exercises. We tried to encourage the readers to find their own answers in the REPL, right? That's what GHCI is for, right? That's what we use it for. And to experiment with things. So there were a lot of places in the book where we said, you know, here's a little example. Now try changing these things about it and see what happens. Because that process of formulating hypotheses about something and experimenting with them means that they come to understand it themselves so that their knowledge is already internalized, right? They get the insight at the same time that they're getting the understanding. And finally, it's important to show failure cases and discuss them and discuss what happened, what went wrong, and how we can fix it. So most people who write blog posts are not very good about doing this, but there are a couple of bloggers that are really, really good about it. So one of my favorite blogs is written by Mark Jason Dominus, who you might be familiar with. I don't know, he wrote Higher Order Perl, and he's also a Haskeller. He actually wrote the famous Monads Are a Burrito post. And I love his blog so much because so many of his blog posts are him having something has gone wrong, particularly with Git, as things will with Git. And so something has gone badly wrong with Git. And he, who has been a programmer for, I don't know, 20, 30 years, something like that. I don't know how old he is, but a long time. And he doesn't know what's gone wrong. And so he actually details the process by which he figures out what went wrong and fixes it. And that's so important. The chances that I will ever have this particular problem with Git that he had are very low. So the answer, the solution to his problem is not what's important. It's the process of figuring out what went wrong. Okay, so let's look at some concrete examples. So when I say give an overview, I'm mostly talking about when we're talking about documentation for an entire program or library. One thing that people often don't do in their documentation is help their readers find the entry points to the program. You assume that, or people assume that your readers will be sort of familiar with a kind of common Haskell layout and will know how to find where the important points of entry are. You should not assume that, because not everybody will be. It seems so basic. It seems like everybody should know that, but in fact, it's difficult. And help them also understand how all the parts are going to work together, right? So you've got, especially in a big project, you've got all these modules. How are these all going to, come together? What's the importance of all of them? So this is actually documentation that I've been writing for my next book called The Joy of Haskell. We have, I don't know, a large-ish, medium-ish, I don't know how big it is. We have all this code that builds the book. This code, this particular piece is the documentation for the building of the book. So we had a make file, and I said, oh, but this is a Haskell project, so we should have a shake file. So now we have a make file and a shake file. And so I wanted to document. I think eventually we're going to release our book building code as a program that other people could use for writing other books. And so I've been writing documentation for it. So the first thing I start with is telling them to look in the package.yaml file. We've used HPAC instead of Cabal or Stack for the project, for the package, packaging. Yes, the package definition, thank you. And so we don't have a Cabal file. We have a package.yaml. So even an experienced Haskell programmer would be looking for like a Cabal file, right? And it's not there. And if you're not familiar with HPAC, then you might not know to look for this thing. So that's the first thing I want to tell people. And the dependencies and the executable names and all of that are in there. Then we're going to look at the shake file itself, right? And that's where the actual building of the book happens. So then I also don't assume that whoever is reading this knows what shake is, right? Not every Haskeller really knows what shake is. I didn't really know what shake was very well until we started doing this, but it's been really cool. So I have sentences throughout the documentation that are comparing it and contrasting it with make, which probably more people are familiar with. Then I went through, so the shake file is a bunch of, well, there's a bunch of stuff in there, but the main part of the shake file is a bunch of do blocks that are all quite similar. So I gave an overview of how all of those are structured. And then I tried to give a sense of how our project itself is laid out. We have code snippets in a snippets directory. Those are Haskell files that sometimes have tech mixed in. They're parsed into tech files by the Haskell detect program, which is why the shake file needs to install, right, the Haskell detect program so that it can build the book. So we're testing all of the code that's going into the Joy of Haskell as we go along, which is really nice, but it makes this extra step in the shake file. And then I said we bring all the files that are necessary to build the book into a flat directory called out. Some people would choose to make a subdirectory, right, for the binaries instead of giving them the extra bin extension, but we kept the directory flat. And then I provide I guess that got cut off when I made the slide, but then there's a little rationale for why we decided to do that. And you might want to do it differently if you're going to use this project. All right. Next, working from concrete examples so that students can build up their own understanding. This is some code that we were writing in my meetup group. It's, this is not very complicated Haskell code, but I was writing it with a group of Haskell beginners. So we have, at the top, we have the whole program, because I should give an overview, right? I should follow my own advice. The whole program we were writing was to validate usernames and passwords, right? So, and then we're going to incorporate that into a yet larger program at some point. So we have a function at the top to strip any leading white space or punctuation from the username, right? And it's recursive, so if the whole thing is white space, then it's just going to give us back a nothing. And if at some point we return some kind of characters, then we get to just whatever's left after the white space and punctuation have been stripped. Then we also wanted to have a maximum length for our username and password. So we have this validate length function. And then we have some new types here, right, for username and password. And I know they're just wrappers around string. I know. But then we get down here and I say, okay, now we need to write the make name function, right? So I asked them, do you think that we should do the length validation, right, at the same time that we're stripping the white space, right? Or should it be dependent on the result after we strip the white space? And we all agreed that it should be dependent on the result from stripping the white space and punctuation, right? You don't want to count any erroneous characters against them for their maximum length. So I said, okay, so how do we write this? And they sort of, well, we don't want them to go at the same time, so I don't think we want to use applicative, and we can't use alternative, right? And they were kind of hemming and hawing about it. And finally, one guy said, okay, I know this isn't real Haskell, this isn't good Haskell, he said, but I think we could do it with like nested case expressions. And I said, yeah, that's totally fine, right? We only have 2 things here, so we can just nest them. This is perfectly valid Haskell, right? It works. But putting this up on the screen for them, having them write it and putting it up on the screen for them, made several of them all of a sudden go, oh, wait a second. We have things we want to happen in a sequence where the second thing is dependent on the result from the first thing. Is that monad? And I said, oh yeah, it is. So then we rewrote it like this. And then because they had that insight themselves, it wasn't me teaching them, this is what you use monad for, although of course we have done that, right? Because they had that flash of insight, now they own that. They totally understand what monad is for. It's an abstraction, a generalization of that pattern that, oh, yeah, actually I do see this all the time. And now they see monads everywhere. So, if you can work people through examples like that so that they can own that insight for themselves, it's great. All right, so encouraging hypotheses and experimentation. This is a thing that happened on Reddit. The gist of this question is actually really an interesting question. It's a beginner question. This is the Haskell questions subreddit. But what I wanted to point out is that the questioner starts off saying, I was looking at the type signature of the return function. Because I don't know what a monad is, the type signature for return caught me a bit off guard. I stared at it for a bit, and it occurred to me, right? So we're already in hypothesis formulation territory. Then he says, I'm just making a bunch of stuff up right now, so help with the terminology would be great. But more importantly, is the mental model correct, right? So this is a great student, right? This is like what you want in a student because they are totally willing to put hypotheses out there and see what happens. But even better, a fantastic person named Iceland Jack answered this question by not answering it. Look, there's no answer, right? He just says, this is a good question. And then he starts presenting observations. Observations that this student can go and play with and think about and come to their own conclusions as they start to understand monads and types and type constructors better. So sometimes the best answer is not answering the question at all, right? But just presenting them with more ideas to think about. All right, then, I already talked about Mark Dominus's blog, but one of our, there's a Haskeller, an Australian Haskeller named Tim Humphreys, and he also does a great job of this on his blog a lot. This is from his most recent blog post called The Round Trip Property. The goal of this blog post is to teach people to do property testing for round tripping, right? So he goes through writing these parsers and printers that should ideally be a perfect round trip, right? And this is late in the blog post, but he's gone through all this code, right? Writing all these parsers and printers. And then he says, okay, we've got a unit test. But of course, his point isn't for people to write unit tests, right? His point is to write a property test to test this property. So he says, my first unit test passes. That's great, we're done, right? If the property test passes. And unfortunately, the property test does not pass. We do not have a perfect round trip. So he explains, he shows you the failure, right? And then he says, he explains why we're getting this failure. There's an ordering problem where we have something that's more general ordered before something that's more specific. So we need to reorder things. And he fixes it, and eventually the property test passes, and we all get to go home. It's really, really important to show people, in whatever medium that you're teaching, to show people these failures. Because we all get them, right? If you only show people your successes, then people freak out and don't know what to do when they get off get off the happy path that you've shown them. We tried really hard in Haskell book to show people Ghc error messages and what they mean, because they can be really intimidating for beginners. They can be really difficult to read. I know there are people who are working on it, right? And speaking of community, right, that's one of the things that Elm has made a really high priority, right, is making really beginner-friendly error messages. We don't have quite the same priority here, but they have gotten better, I think, since I started learning Haskell. But in Haskell book, we tried really hard to show people the error message, how to read the error message and figure out what went wrong and fix it. Because that's going to happen to you all the time, every day when you're programming. All right, now I want to talk, I think I still have enough time. I want to talk about a few of the challenges of teaching Haskell. These are not necessarily only about Haskell, they're also about mathematics. Again, because I find a lot of similarities. One of them is that, like mathematics, Haskell is a very tall subject, right? Concepts build on other concepts. It's perhaps less like a ladder, more like a scaffold in that there are a lot of points of intersection and interconnection. But if you don't have certain base layers in place, you don't understand certain base concepts, then understanding the next level up or the next connections out will be nearly impossible, right? So my good friend, Chris Martin, said that his math teacher, I think it was your math teacher, right? Yeah, used to say this, that mathematics is a succession of trivialities. The problem is that it's the accumulation of trivialities, right? This is saying the same thing, right? That you have to build up these, each thing is sort of small and not that big of a deal, but they accumulate. And if you missed something down here, these later ones will be too hard, right? This quote used to enrage me because I feel like when people say trivialities, they mean that something must be easy, but that's not the point, right? The point is that it's a bunch of small things that build up. Each small thing is not necessarily easy, it's just relatively small. Just like monad is actually a really small thing. And then we have the Haskell Pyramid, which is again the same basic idea, but it's really important to tell people this, that Haskell is very tall, but what you need to actually be a productive Haskell programmer is about where that red bar is, right? You need a fairly wide base, but you don't need to be very high up on the scaffold yet, or the pyramid, right? What you will see people talking about on social media, on Reddit, on Twitter, what you'll see people talking about in Haskell is oftentimes way, way up here. And you feel like, oh my God, I'm never going to understand what these people are talking about. But you will, right? It's just an accumulation. It's just an accumulation. And if you keep building up, if you get to that red bar so that you're writing Haskell programs, the accumulation will start happening faster and faster in my experience. And eventually you will know what all these people are talking about, or at least be able to fake it better. All right, so another challenge with teaching both math or Haskell is that mathematical knowledge in particular is really compressible. I don't know if I'm making up the word compressible, but once you understand something fully, you can kind of file it away as some bit of knowledge, right? You can file away some proof or some, for all of us, well, I don't know, but for all of us, there are some beginners here, I think. But for most of us now, right, monad has become this compressed bit of knowledge, right? We just know how it works, and then it becomes hard to explain to people, right? Once you've compressed that knowledge, you don't remember the process you had to go through to understand it. You've already got the insight. And expanding that into an explanation of the understanding that you had to go through to get that insight is really hard. And that's the process of teaching, but it's a really hard thing to do. So, then sometimes it happens that you just see something and it sort of immediately gives you the flash of insight and you never have to go through the work of understanding it. So for me, when we were writing Haskell book, we kept talking about applicatives being monoidal functors, right? This is a difficult thing to talk about because the monoids are implicit. But for me personally, as soon as I saw this example, or an example like it, when I saw how the tuple applicative works, it was just an immediate flash of insight, like, oh, I get why applicatives are monoidal functors. I just get this. It seemed completely obvious to me. I have since discovered that this does not make it immediately obvious to everyone else. And so as a teacher, I've had to recreate, or not recreate, create some process by which I can explain this to other people to whom it is not immediately obvious. But if you do get these flashes of insight, and I think they happen a lot if you're a really experienced Haskell programmer, it can be really hard to figure out some way to convey this information to other people in a way that makes sense to them. All right, oh, and then there's the next thing. And this is also a really hard thing. It's that when you reach a certain point of competence with something, especially if it's something that you really love, you want to share all of your knowledge with every new person who will talk to you, right? So there's a thing that happens when you're learning Japanese. You say, okay, I'm a beginner in Japanese and I'm going to learn how to count to 10. And someone who knows Japanese and has been studying it for many years and wants to demonstrate to you how competent they are at Japanese will come along and tell you, no, counting in Japanese is so hard because there's all these counters and you have to know all these suffixes that go with all these different types of objects. And so you start feeling like, oh God, I just want to learn how to count to 10. You know, what's the big deal here, right? They're not wrong. All these counters exist. So we count to 10 in Japanese, or let's say we'll count to 5, right? Ichi, ni, san, shi, go. And then we're done, right? That's not hard, and you can learn that in, 10 minutes, less. But it's true that to count stuff, or to count people, or to count animals, Japanese makes all these distinctions of size and shape and animacy, right? And so, like if we're counting Lego bricks, we count them ikko, nikko, sanko. We're counting people, hitori, futari, sannin. We're counting sort of shapeless things, or if we don't know the right counter, we fall back on these. Hitotsu, futatsu, mitsu. Now, in fact, you can go to Japan and you can tell somebody, say, san ringo, ringo means apple, and they will understand what you mean, right? So in fact, if you never learn all the counters, you can probably still communicate in Japan. If you learn maybe 3 or 4 of them, like it's fairly important to learn the people one because it's considered to be really rude to count people as if they were objects. But you can get by without knowing a lot of these, right? So this thing that people do because they're excited about how interesting this Japanese system is and they want to share that knowledge with you, but it's really intimidating when you're a beginner. And I find that we do that a lot in Haskell. I do it all the time with monoids. I get people who are asking me very basic questions about monoids, and then I end up wanting to talk to them about how some types and product types are duals because types are a monoidal category, right? And I get really excited about it, and that is not what they need, right? I'm basically telling them that they have to learn how to count whales in Japanese, right? All right, so the next book that I'm writing is hopefully designed to help smooth that transition between feeling like, okay, I'm down here on the pyramid and I can write some Haskell programs and I'm feeling kind of good about myself. And then I look at Reddit and people are talking about, pro-functors and all this stuff, right? And I don't have any idea what they're saying. So the next book is sort of designed to help smooth that transition and is called The Joy of Haskell, as I'm sure many of you know. And we are hoping to make a sort of guidebook to get you more comfortable with the larger Haskell ecosystem, which will include the Ghc extensions, a bunch of libraries, and the wider world of various functors and a little bit of category theory, a whole bunch of set theory, maybe a smattering of lattice theory, right? So that you can be familiar with the kinds of things that people are talking about on social media, and maybe the pyramid will look a little bit less intimidating. So I've relied a lot on comparing teaching programming or teaching Haskell to teaching mathematics. But I want to leave you with this thought from Dijkstra, not just because Dijkstra quotes seem obligatory, but also because I think it's an interesting, I've been thinking about it a lot, and I don't know the answer. He says, a programmer has to be able to think in terms of conceptual hierarchies that are much deeper than a single mind ever needed to face before. Compared to that number of semantic levels, the average mathematical theory is almost flat. And I don't know the answer of whether or not teaching programming, really teaching programming, is harder than really teaching mathematics. To me, they feel very similar, but I could be wrong. So this is something that I think about quite a bit, and I want to leave you with that. Or actually, I'll leave you with the references in case you want to read the things that I've been talking about. I particularly recommend the two papers by William Thurston, neither of which is long or difficult. William Thurston, I guess he would know a few things about theorem provers getting all the recognition and credit because he's won a Fields Medal and all kinds of stuff. But he had a lot of really great things to say about teaching math. Okay, are there any questions or comments? Yes? I can't help you with that,
though. Okay, my question is why Haskell, though? You have a lot of languages that are sort of more practical in the sense that you can get stuff done quicker, and you have languages that are actually theorem provers like EGDA or COC, where you can express all those abstract patterns that you care about, like why applicatives are monoids. You can express it in the language directly. And then Haskell is in between. What do you think makes Haskell so good for teaching beginners to think mathematically about programming?
That's a really good question. So for me, the reason that I became interested in Haskell before I became interested in, say, Idris or COC, right, is just that I was introduced to it first, right? I never heard of Idris or COC until after I came to Haskell. But in terms of teaching other students, well, again, that's part of the issue, right? They've heard of Haskell, at least, whereas a lot of the dependently typed or theorem-proving languages they haven't even heard of yet. A lot of people sort of go to those languages from Haskell. Not everybody. So that's part of it. Part of it is that most of the time they do want to understand new ways of thinking about programming, but they also want to be able to write practical programs, right? And so while some languages might be better for spreading the love of pure logic and mathematics, Haskell is going to be more attractive to, I think, average programmers, and incidentally, they will get to write some programs, and incidentally, they'll come to love monoids and monad. I mean, everybody does, right? Everybody starts to love monoids after a while. I'm convinced of it. Yes?
What do you think of Elm, like first exposure to programming or a language for teaching programming in general, like before Haskell or?
So that's also a good question. I don't have a lot of experience with Elm. I don't really do anything front-endy that I would use Elm for, so I don't have a lot of practice with Elm. But I think that I really like the Elm community. I'm going to be a little controversial here, I guess. I really like the Elm community. I really like their emphasis on being welcoming and friendly to beginners. I really love what they've done with error messages. I really hate that the reason they've done that with error messages is because they got rid of type classes. So you can have my type classes when you pry them from my cold, dead hands. Yes?
As a programmer that has been brought up with imperative languages, I find it quite difficult getting into functional programming. have you noticed any difference between people that never programmed before in how they learn Haskell compared to people that have learned, say, C++ or something like that?
Yes. Yeah. People who've learned an imperative language before almost always want to draw as many comparisons to the languages that they already know, and it doesn't always work very well for Haskell. So one of the biggest is when they're trying to understand type classes, and I've written about this before. One of the biggest is when they're trying to understand type classes and they want to make them, they want to understand them to be just like Java interfaces, and it's sort of similar, but it's not exactly the same, and there's enough significant differences that I think it's harmful in the end, and you kind of need to try to understand Haskell, like if you could push your other programming languages to one side, right? And I think of it like, I was a language teacher before I started, natural languages. I taught English as a second language in particular. And when you get training to teach second or foreign languages, you are taught that the best way to teach them is through immersion, right? So people should be listening to and speaking the target language as often as possible. So as much of your class as you can manage speaking the target language so that the students are hearing it, even if they don't understand every word. They're hearing only, I taught English in Japan, so I would do my whole class in English, right, and never speak Japanese to the poor children. And even if they didn't understand everything, the fact is they're hearing all of the English, and that gets them into a mindset where they're trying to think in English rather than translate from Japanese to English in their heads, which is a much slower and more error-prone process. And I kind of think about teaching Haskell the same way. If I could put you in a situation where you couldn't hear or see any, Java or C++ for a couple weeks, and you could only do Haskell, like get you thinking in that mindset, that would be a lot more effective. But it's hard, yeah. Yes. Oh.
Hello. Right, not a question as such, more of a comment. Thanks for the great talk.
I don't know who's speaking. Oh, hi, sorry.
Right, so thanks for the great talk. And I've done some teaching of Haskell at Helsinki University, and my experience about teaching monads is exactly the same as yours. So I try to let people write out these painful nested case things and then maybe come up themselves with, like, the utilities to make writing those slightly less painful. Yes. And then when I show them the monads, they're like, oh, right.
Yes.
So, yeah.
Yes. Oh, this is exactly what we needed. Yes. Yeah.
But yeah, thanks.
Yeah, thank you. Yes? Yeah.
Hi, is this loud enough? Right. I have been teaching Haskell at ETH to second-year students, and I've noticed that a lot of them get really frustrated by how long it takes to solve type errors, and then don't recognize that they've actually saved themselves time in debugging afterwards. Yeah. Have you found a way to tell them that in such a way that they'll understand and
Yeah. Yeah, I think that's a really good point as well. Because I think that one is a little bit more difficult for me because I've never been a working programmer. So to me, debugging means nothing, right? I don't debug anything. So, but that's a really good point. I think you're right. Yes.
I wonder if you'd like to comment. One of the problems of equating maths and Haskell is the fact you've got lazy evaluation. Yes. So you've got lots of partial and undefined values sitting around. Is that something that you've found a problem in practice when you talk about things being monoidal? They're monoidal when you look at the total subset, but is that, and I know people in the past who found that impedance mismatch between total mathematics and partial computing to be tricky, and I wondered how you dealt with that.
So since most of my experience is teaching mostly fairly beginner level, that's not something I've run into a lot because they're not at a level yet where they notice. It takes, I think, a little while before they start to notice that and find, there are other there are other things that make Haskell not just like math, as much as we'd like it to be. But yeah, and that can be a problem when you're teaching more advanced students, and you just have to, well, that's mostly what I do, is I just tell them, well, Haskell's not just like math because we have to deal with computers, right? Mm-hmm. So, yeah, but I haven't found that it's been a problem yet.
Okay, thanks.
Anyone else? Yes?
Question is my another question is how to deal with students that don't have the temper to learn of all of the Haskell Pyramid before they want to see useful results. I was teaching Haskell to a bunch of students, and I decided to do it the hard way. So before introducing parametric polymorphism, I had them copy a few functions for various monomorphic types. Mm-hmm. Before introducing type classes, I had them pass the explicit dictionaries to those functions. And before introducing monads, I had them write those nested case expressions. And in the middle of the course, students decided that Java is better.
Yeah, well, I think just recently I've had a student decide that as well, and she hasn't come to meet up again, but unfortunately. But yeah, I mean, that does happen, and so sometimes you can do this, I think, a little bit more when you're live teaching, because you can sort of read your students. And so if I get the sense that this is becoming too much, boring struggle, then I start sprinkling in new exciting things, right? Things from a little higher up on the pyramid, like, okay, you're not going to have to do this forever, right? I promise that we're not going to be writing manually recursive functions forever. We're going to get to folds real soon, and then you'll never write manual recursion again. Yeah, that definitely is a problem, and you just have to. I think that just comes from experience of interacting with students and being able to tell what their tolerances are, and that's not something I have an easy formula or answer for.
Let's thank the speaker then.